So today we're talking about random variables. Make sure you guys get down your goal. You'll be able to define what a random variable and the expectation of a random variable. Now today's lesson really isn't that bad. It's kind of an extension of what we've been talking about. So hopefully, we'll be okay. All right. So a random variable is a quantity whose value depends on chance, solely on chance. That is what a random variable is, okay? So it's not none of these like, he could do X, Y, no. You gotta take that whole idea of, well, this could happen out of the question, okay? It's solely on chance. Random variables are represented with capital letters, okay? And what you see below are examples of those, okay? You don't really have to write down the examples, but basically they're all capitalized, italicized capital letters. Such as, X is the number of sixes obtained when the dice is rolled 3 times. B, the number of babies in a pregnancy. M, the mass of crisp in a packet. T, the time taken for a runner to complete 100 meters. So on and so forth, okay? So they're represented with capital letters. So basically with random variables, you're going to be finding the probability of these different types of situations. Now honestly, random variables, like you guys probably have done probability problems that dealt with random variables and you didn't even know it. Like you're going to be surprised to see the similarities between it, okay? That's why I say this lesson is pretty easy. It's just maybe the wording might throw you off and really it's just what we've been doing, okay? There are 2 types of random variables, which we talked about last year when we first went over probability, but I didn't go back over them this time around because I guess I forgot. But luckily it came back up. So we have discrete random variables, which have a finite or countable number of possible values. And then you have continuous random variables, which can take on any value in some interval. Okay? And what we're going to do is, before I finish off the rest of the slide, we're going to do some practice to see if you guys can recognize it when you have a discrete random variable over a continuous random variable. So if you look at those examples I gave you on these random variables, X, the number of sixes obtained when the dice is rolled, is that discrete or continuous? Write it on your whiteboard. Are you writing a D or are you writing a C? 3, 2, 1, hold it up. Yeah, come on. It is discrete because you can actually count those out. Now realize that, if you do this roll 3 times, you can actually count those out. What about B, the number of babies in a pregnancy? Is that discrete or continuous? Write it down. Write it down. You're either writing a D or a C. And hold it up in about 4, 3, 2, 1. Hold it up. That is discrete. The number of babies in a pregnancy, we can count. You're either going to have 1, you're going to have twins, triplets, or you're going to be like the octomom that had 8 at one time. Okay, but they're countable. What about M, the mass of crisp in a packet or a bag of chips? Is that continuous or is that discrete? You're going to write a D, a C. Which one is it? Hold it up in 3, 2, 1. Hold it up. It looks like we're almost split here. That is continuous. Mass, weight, those things cannot really be counted. It's an interval. It can weigh between 0.25 grams all the way up to, it's a range of values that it can take on. So that's why mass and weight and things of that nature are continuous. What about the time taken for a runner to complete 100 meters? Is that continuous or discrete? Hold that up in 3, 2, 1. That one is continuous as well. Time is definitely an interval, guys. Time is definitely an interval. It could take someone anywhere between 13.4 seconds all the way up to 9.9 seconds. Okay, it's a range of values.
So babies aren't continuous because you can't have
like you can count them as they're coming out. 1 baby, 2 baby, 3 baby. You can count those out. But time is always an interval.
So stuff you measure?
It's stuff that you measure. Yeah. Stuff that can be measured is that. So like weight, mass, time,
can't look at it.
like length.
Like for instance, if it was saying the amount of runners to be able to complete 100 meters, that would be.
That was
just
the
a number of. Yeah.
Alright, so here we go, we're gonna do some more, okay? Here we go.
Wait,
No question.
so like, if it was time, it would be continuous, but if it said like the number of seconds it takes, would that be,
That would be the number of seconds that it would take.
like, the number of seconds a run takes?
That will still be continuous because it's still time. But that does have the number in front, so you can say that's discrete. Alright, here we go. The number of hairs on a Scottish Terrier. Is that continuous or discrete? You're gonna hold up a C or D in 4, 3, 2, 1. Hold it up. That one is discrete.
Is where they count as they grow.
It is discrete, even though there might be a lot of hairs to count. The thing is that you can separate and go 1 hair, 2 hairs, 3 hairs, 4 hairs. No matter what, that is still countable. You can count all the hairs and get a number. So that was discrete. What about the height of a building? The height of a building. Is that continuous or discrete? You're putting a C or D. Hold it up. It is continuous. It is continuous. All right, here's the next one. That's my pen in my pocket. Here's the next one. The amount of fat on a steak. The amount of fat on a steak. You're gonna write down a D or a C, and you're gonna hold it up in 5, 4, 3, 2, 1. Hold it up.
That looks like a bean.
It is continuous. It is continuous. I hate fat on a steak. I really do. Here's the next one. A high school student's grade on a test. Is that continuous or discrete? A high school student's grade on a test. Continuous or discrete? You're going to write down a D or a C. And hold it up in 3, 2, 1. It is discrete. It is discrete. Because you're right, a class's grades could range between a certain value, but your grade on the test will be an 88. It's something that is finite. Okay? What about the number of fish in the Atlantic Ocean? The number of fish in an Atlantic Ocean. You're writing a D or a C, and you're holding it up.
And Atlantic.
In the Atlantic Ocean. What's wrong?
Well, no, like.
I said it wrong.
Like. No, I was just thinking, like, in an Atlantic Ocean, like, there's more than one Atlantic Ocean.
In the Atlantic
That's
Ocean.
ridiculous.
Hold it up. Hold it up.
Like, the amount of fish in the Atlantic Ocean is ridiculous.
Good job. It is discrete. Now, there might be a lot of fish, but we can still count them. What about the temperature of a wooden stove? Is that continuous or discrete? Is that continuous or discrete? Hold your answer up in 3, 2, 1. That is 100% continuous. Yes.
Oh, I'm gonna put D.
Okay, so remember, anything that you can physically count is discrete, or range, the interval of values is continuous. So are we okay with that?
So if you can't count it, it's continuous. Can't count it in numbers.
Alright.
Like 1 height of building. 1 height of building.
Alright, so how do you represent a random variable? It's right here with this notation. The probability of your random variable equals x, where x is the actual measured value. So this lowercase letter, that lowercase x, will actually represent the actual measured values. Okay, and the example that I give to you here is that the random variable x from the last example, the lowercase x represents the probability that the number of 6's is x, where x can take on the values of 0, 1, 2, or 3. Okay? So basically, you have die that you roll 3 times. Well, x can represent the number of 6's. Scratch that, start over. The random variable represented the number of 6's that are rolled in 3 times. So lowercase x would represent, rolling no zeros, 1 0, 2
6?
no sixes, 1 6, 2 6s, or 3 6s.
So it
I'm
would be
off
like
today.
6 equals 1, 2, or 3.
0.
Your x would equal 1, 2, or 3. The x represents 6 showing up on
And
those
then the
3
big
rows.
X
Would be the probability of 6s occurring. Okay? So what we're gonna look at now is an example. No, a little bit more. Okay? Well, actually, we are gonna look at this example. A probability distribution for a discrete random variable is the list of each possible value of a random variable and the probability that each outcome occurs. So we are gonna look at that situation for this random variable, and we're actually going to solve it out. We are gonna make a probability distribution, okay? Of that particular random variable x.
1 through 1.
So we are gonna look at this situation. We are gonna let capital X be a random variable that represents the number of 6s obtained when a fair dice is rolled 3 times. We're gonna tabulate the probability distribution of X, okay? So, I'm gonna need this space here. So a probability distribution looks like this. It basically looks like a table where X actually represents like the outcomes that could occur. No 6s, 1 6, 2 6s, or 3 6s on those rows. And then the second row would represent the actual probability of these particular situations happening. That is a probability distribution. Okay? So, the best way to do this is, what do you think? To show this out. These 3 rows. Tally marks. You want to write out the possible outcomes? Or we can do a tree diagram.
Or the little dot thing.
Not so much a dot thing because we are dealing with 3
What is it?
flips versus 2. Instead of the sample space, we have 3 things there. We're rolling it 3 times versus just 2. We could do it if it was just 2. So the first row we could end up with a 6 or not a 6. Okay? Now if we do, that's on the first row. Okay? What is the probability? 1 6 and 5 6. So on my second row, I can have what? You can have a 6 or not a 6. Now, does my first row have anything to do with my second row? So they're what kind of events? Independent. So whether I get a 6, my second row I still could get a 6 or not a 6. Or if my first row was not a 6, I could get a 6 and not a 6 still. And my probabilities are 1 6 and 5 6. And no matter what, remember when you're doing a tree diagram, your branches should equal 1. Stay good. Now my last row, no matter what my first 2 rows were, it has no impact on my third row. I'm still going to end up with a 6 and not a 6. A 6 and not a 6, no matter what, I ended up on my first 2 rows. Now realize they probably not going to give you something like this on like a non-calculator one that's going to be any bigger than this. Okay? So do realize that you could go out this far and it still be fair game to be on the test, especially on a non-calculator. What we do on Monday, we'll talk about when they are like really big. Okay? You are rolling a die 12 times and you're trying to figure out the probability of getting ahead 3 times. Okay? We will do that on Monday.
I get it now, because it's a 1 2
Is it kind of like binomial distribution where you like?
Yeah, I see it.
That's fine. So here we go. What is the probability that I get no 6s? No calculator here, guys.
At all.
6.
No 6s.
Most of it.
25.
On my 3 rows.
36, 36, go.
625.
125.
Oh, 125.
125 over,
6 kilos.
we're looking here. Not a 6, not a 6, and not a 6. That's what we're looking to figure out if we don't get a 6 at all.
At 216.
That is 216. Remember, you guys should know your powers of 6 at least up to 3. This is fair game. This is fair game. Let's do the next easiest one. you get all sixes. What's that probability?
1 out of 216.
1 out of 216. That is the very top branches. That you get a 6, and then a 6 3 times. Now for the inside ones. I'm looking for, I get just 1 6.
That's 25 out of, no.
Guess
Well,
for
let's
one
see. I
branch.
could get a 6, and then not a 6, and not a 6.
Yeah,
That's 75.
Or I could get not a 6, a 6, and then not a 6 again. Or not a 6, not a 6,
And then 6.
Not a six.
and then a 6. Those are my only outcomes where I can get just one.
Okay, that one is 25 over.
That's 75.
The first one is 25 over 216.
They're all the
over
same, so
25.
it's 75 over 216. Jonathan.
Awesome. And now, instead of trying to count all the possible combinations of me getting 2 6s and only one not a 6, I could do
15 over 216.
Subtract
it
From 216. You add them all together and you subtract from 216.
exactly, because no matter what, still, all of these probabilities should add up to be 1. Or 216 over 216. So what is that? What's 125?
201.
201. So the last one is
15.
25. 216.
you could also again go through the process and actually do 2 6s and not a 6. But there you go. There's your probability distribution.
It seems like exactly what we did before.
Just represented in a different way, right? So that's what I'm saying. It's not hard. Let's look at this next one on your whiteboards. Okay, whiteboards. Am I still recording? Sure. Okay. So I want you guys to read this out. All right, hold on. Am I gonna do? Yeah. And this is one on the whiteboard. I want you to kind of give it a try. You are making another probability distribution table, and then we'll check it. So for this particular one, if X represents the number of houses with dangerous levels, what are those outcomes?
0, 1 house, and 2 houses.
Okay, go ahead.
Is it just 2?
Because there are 2 houses that they chose, so either none of the houses have the dangerous levels, 1 house, or both houses. So the probability, our random variable, X equals lowercase x. What was the probability that none of the houses had the dangerous levels? 4 out of 9, 1 house,
4 out of 9.
and both houses.
1 out of 9.
Because if you really think about it, it said that the rating level is 1/3 of the houses in the area. So if the first house had it, that would have been 1/3. Second house had it, that'd be 1/3 as well. Their probability. So you multiply them together to get 1/9. Okay. So if none of the houses had them, that means that it would be the complement, 2/3. 2/3 for the first house, 2/3 for the second house. You multiply them to get 4/9 for none of the houses, and of course, 1 apiece. It'll be 4/9. Good stuff. Back to your notes. For any random variable x, always remember that the probability of the random variable happening is again between 0 and 1, and then the sum of all the probabilities should equal 1. So that's one way you can always double check to make sure that your probability distribution table is correct. All your probabilities should add up to equal 1. Just like before when we were looking at our Venn diagrams and our branches of our tree diagrams, they all need to make sure they add up to equal 1 as well. Okay? So we're going to look at this example here, sample IB question, and then we're going to look at a few others on your whiteboards, and then move on to expectation.
Is the E symbol a sum?
Yes. This particular thing, yeah. So, what you guys get for the value of C? 1/20, very good, because 7 plus 5 plus 4 plus 3 plus 1 is 20C, and all of those should equal 1. So then you divide by 20, and C is 1/20. So what is the probability that X is greater than or equal to 4? So X is this probability distribution. So what is the probability that is greater than 4?
1/5.
It would be 1/5, because this particular probability for your random variable is greater than or equal to 4. You're basically looking at this part of your probability distribution table. You just found out what C was, so that's 3/20 plus 1/20, which is 4/20, or
I literally didn't even get there.
1/5. I should get that.
I didn't get there, and then as soon as you asked, I just did it.
There you go. Simple enough, yes?
Intuition.
Intuition.
Whiteboard time. Take a look at this one. If you're watching the video, pause the video, because then I'm coming back with the answer. I want you to write your answer on your board. And justify your answer. Okay. Yes, this is a probability distribution. I asked you to justify your answer because that can very well happen on your IB exam. And you know the reasoning thing is kind of left up to judgment. Okay? If you know that the probabilities all have to add up to equal 1, okay? You need to make sure that you say that. Now, you can either state that by easily saying that the sum of all your probabilities equals 1, like how it was in their previous slide, or you would need to have, in some shape or fashion, just make sure, be careful on your wording. Some of y'all's wording was a little off. I'll say that much.
So what
Okay.
wording would you have to say?
I would say to be sure that you would make sure that you got all the full points. I'll try to represent this. This is kind of like a setup formula there. Definitely make sure that you can't say anything because it said so or because everything's already given to you. Just be careful on those type of things. Okay? Just be very, very careful. All right? Use your notation, things of that nature. Now, one thing that Jacob, I did see on yours, and it reminded me to make sure I mentioned this, is that, yes, this notation right here can also be represented like this or like that. Okay? So all three of these notations mean the same thing. Okay? So they're interchangeable. So I saw that you did use P of X. That actually does correspond to the random variable. So, good stuff. We got one more. It is related to this problem on your whiteboard. Okay? What is the probability that a randomly chosen student receives a B or better? What is the probability that a student receives a B or better? Got it. What is the probability? Hold it up. Now I have seen people not get credit for this because it asks you for the probability. One half. Oh yeah. Yeah, one half would work. But I also saw this. Okay? So be cautious there.
So it wasn't a trick question, it was a trick location.
Yeah, that will work. And how that would be represented using a B or better? That's how you would write it. That's 0.5. That'll be your proper notation. Okay? Questions on probability distributions? Huh? Expectation. The mean or expectation value of a random variable x is the average value that we should expect for x over many numbers of trials of an experiment. That is represented by a capital E, parentheses, your random variable, and is often denoted by mu, the Greek letter mu. Okay?
Oh, that's what that is. I thought it was you.
That means mean. Both of these represent mean or expectation. So, looking at expectation, this is your formula set up. You don't have to write down the extra little bit, but that's basically what it breaks down to be. The expected value of a random variable x, and again, it could be any capital letter to represent a random variable. but E of X equals the sum after you multiply each value by its respective probability. Okay? That is your formula for expected value. We have done something similar to this when we first went over probability. Okay? It's just now, since we have different outcomes that could happen, we're going to add up all of those values. Okay? Not so much. It's like when you're looking at your probability distribution table. Okay? Take for example, actually I think I'm going to do it on the next one. Example right here. Everybody have it down? Alright. So using that first example, what is the expected value of X? So that first example I'm referring to is the one about the sixes. Okay? Remember how we have no sixes, 1 6, 2 6, and 3 6 with their respective probabilities? Which were 125 and 15 and 1. Okay? So to find the expected value of X, you would take each one of your X's, 0, and multiply them by their respective probabilities and add them up. That is how you would find your expected value. Again, this is still being done without a calculator. 0 times anything is. We have 75 over 217 plus, 216. 30 over 216 plus, which all add up to be a total of 108 out of 216. So out of all the possible types of combinations we could have, those 216 possible combinations we could have, 100, that's the expected value for us too. What?
Like, what is an expected value?
Is the average value that we would get over a certain number of trials. Okay, so if we were to roll this,
How would you write?
it would be E of X equals 108 over 260.
Wait, what is the 108 over, what is that?
That represents the expected value of you rolling a 6 in 3 rolls. That's the expected value.
All of it?
Mhm.
Oh.
That one half.
This is kind of used a lot in
Yeah.
like.
So you,
No,
3 over
I didn't.
Yeah, well,
Yeah.
if you understand gambling.
so you would just expect
No,
there is a
because-
lot more than just 6s a bunch of different times. You would
Look,
expect
expected.
most of the time.
One-
well,
depends on
one
one
is
six
one
times
or
30.
Yeah.
Oh, so the expected value of not rolling
1
six
6
would
times
be
3.
108.
Like, if you're playing Texas Hold'em,
So it's basically
1 6,
Yeah.
you do it 3 times,
Okay.
add them up.
That's weird.
That's true.
So to bring it all together, you remember your problem of the day? What's the problem of the day talking about?
Jose, riding the bus.
Catching the bus, missing the bus, being on time, being late. You have all those probabilities, right?
In mind.
I want you guys to do this on your whiteboard.
3 euros.
So the cost for each day that Jose catches the bus is €3.
Jacob,
There's-
Jose goes to school on Monday and Tuesday. Copy and complete the probability distribution table, and then find the expected cost for Jose.
Or notes
Both.
or-
I just wanna say,
Do this on your whiteboard.
this is the absolute worst.
So bringing it back all together from your problem of the day that dealt with Jose catching and missing his bus. He has to pay €3 for every time he catches the bus, and he catches the bus 4 nights, for 1 day, either Monday or Tuesday, and then also 4 over 9 if he catches it both days. So him paying $6 for both days or $3 for one of the days. Okay, and remember that, like some of you guys said, that was based off of that very beginning. He had 1/3 that he would catch the bus, 2/3 that he would, 1/3 that he would miss the bus, 2/3 that he would catch the bus, right? So this is for Monday. The same situation happens
3 would mean that he catches it at least once.
on Tuesday. Okay? So you still have the same probabilities. And so then you would look at those to determine, okay, well, if he's only paying $3, that means he's missing it one of those days. So you're looking at E and E complement, or E complement and E. That's what you're looking at to find for the one in the middle.
They're both 2 over 9s.
And you got it. And then over here, you give 4/9 for he catches it both times. And so then to find the expected cost of both those days, you would have to use that previous chart, and you will multiply 0 times 1/9, 3 times 4 nights, and 6 times 4 nights to get a total of how much you would have to pay for both those days, which is
36
for what? Euros.
Doesn't make sense.
That's what he's expected to pay, at least $4.
Yeah, it doesn't make sense.
But.
Oh, at least $4 makes sense.
Yeah.
$4.